Hello everybody, my name is Marcia Han. I will be in this lecture teaching you about deep learning, the fundamentals 101. So the presentation is going to be focused on the following, the outline. I'll cover the history, the neurons, deep learning, the training, hyperparameter selection, gradient descent, confusion matrix. Once these basics are taken care of, we're going to learn some deep learning models that are famous, such as CNN, convolutional neural network, LSTM, long short-term memory, GANs, generative adversarial networks, autoencoder, transformer. After that, I will talk about what to do now, ensemble learning, transfer learning, hybrid, and also Python. Then I'll give a little blurb about deep reinforcement learning. Finally, I'll do deep learning applications in power systems and smart grid. And then I'll discuss a bit about the future with quantum machine learning, and then I'll share with you my references. So, deep learning actually is not a recent thing. It actually started in the 1940s. Um, and in 1943 is when the first concept of a neural network actually started, the neuron. So anyways, there has been an explosion with deep learning the past decade, and the main reason for that is because we have the memory and the computational power to do these massive calculations, which is something we didn't have before. And we can see that the latest innovations include LSTM, GANs, and other concepts as well. So fundamentally, deep learning is consisting of neurons. And what neurons are is that it's a mathematical concept that tries to replicate an actual neuron in our brain. What it does is that it takes its inputs and multiplies them by weights, adds a bias, sums this all together, sends it to an activation function, and then it produces an output. That's the very fundamental issue of a neuron. So at the beginning, they did neural networks. They had the input layer, output layer, several neurons, but they couldn't solve the XOR function. OR function they could do very easily. It's just a straight line. But the XOR, there's no such thing as a straight line that can separate it properly. So then a few years passed by with disappointments. And then finally people started to come up with deep neural networks. And these are neural networks that have more than one hidden layer. And in fact, by the universal approximation theorem, it was proven that with multiple hidden layers, you can replicate any function possible, any continuous function. Another big issue with deep learning is how do you program the model to learn? And this was a discovery that's quite recent, and that was the backpropagation. Once this discovery happened, then all of a sudden there's an explosion of methodologies for deep learning. Anyways, backpropagation is the following. You program a model, you determine the target and the created results. You figure out the difference, and then you propagate this difference via chain rule at each neuron, okay, at each weight. So then the weight changes according to what the result was. There's also 4 types of deep learning: supervised, semi-supervised, unsupervised, and reinforcement learning. With supervised, what happens is that you have a target classes set that you train with. Okay, semi-supervised means you have some data that you train with targets and some data that you don't. Unsupervised has no target at all. You just train and you learn patterns from the data without having something to classify as. And reinforcement learning is a new paradigm whereby you take your experience and then you learn from that. So the activation function I mentioned to you before is the part of the neuron that takes the sum of the weights and the bias together and then sends it to the output. Okay. In the beginning, activation functions were linear, kind of like the ReLU function right here. And they learned that there were some problems here, such as vanishing gradient, gradient explosion, and so on. So they came up with different types of activation functions, such as the sigmoid, the tan, leaky ReLU, max out ELU. And what all these functions do is that they take the information and they squash it to the maximum minimum of the activation function. There's also the loss function, which takes the value that you that the model is able to produce, and you subtract that from the value that's actually supposed to be. Okay, that's called the loss. Generally, the loss function is the mean squared error function. There are other types of loss functions, as you can see here. Another type that's also used a lot is mean absolute error. So they do have rules, general rules, when to use these ones. I'm not going to discuss that here. That is easily available by looking up. Now I'm going to talk about hyperparameter selection. Okay, and why is this important? Well, there's a concept of overfitting and underfitting, and I'll discuss that. We have hyperparameters, which we'll discuss. Other methods of solving overfitting and underfitting will also be discussed, and then I'll talk about how to find hyperparameters. So overfitting and underfitting. Basically, when it's underfitting, it means that the model is not able to capture sufficiently the data. Okay. Overfitting is when the model captures too accurately the data. Essentially, it has memorized the data. So why are these bad? It's bad because you're not able to generalize. Okay, with underfitting, you're going to miss a lot of data because it does not fit the model. With overfitting, you're also going to miss a lot because patterns that should be accepted are not because they don't fit the memorized concepts. So for hyperparameter selection, it includes choosing the number of hidden layers and the number of units. Dropout, which is removing a neuron after training. What also can be done is network weight initialization. You can choose different activation functions. You can choose the learning rate. And the learning rate basically tells you how fast the gradient descent should move at each iteration. We also have momentum, which takes into consideration change using the velocity from before. We have the number of epochs, which is the number of times the whole training data is shown, and batch size, which is the number of subsamples per each update. There's also two other methods called data augmentation and cross-validation. So data augmentation, or also called image augmentation, what happens is that if you don't have enough data, you can take an image and then warp it around, just like this line here, and then each one of these can be considered a new image. Cross-validation is when you have a limited amount of data. So what this does is that it augments the number of information that you have. So you separate the data into buckets, okay? And at each iteration you take one bucket to be the test data and the rest of the bucket to be training, and then you iterate between them. There's also three types of search to determine what type of hyperparameters to use. First one is manual search. So in that case, you have to train by yourself. You test, what learning rate, what dropout, and stuff like that. But they do have algorithms to accomplish this. One is called grid search, and what happens here is that we have a grid of values for hyperparameter 1, hyperparameter 2, and so on. And then it goes and investigates each intersection. With random search, we take the same grid of hyperparameters, but instead of going one by one, we randomly pick different combinations. There's also the issue of gradient descent, which is how is the gradient calculated. So there's batch calculation, stochastic, and mini batch. Which batch, you take the whole data set and you update the parameters. With stochastic, you take one at a time a data point and you calculate the updates. And mini batch, you take a small sample of the total set and you do the updates. So there's this issue of exploding and vanishing gradient descent. Exploding, what happens generally is that the slope gets larger and larger and larger, and vanishing is the opposite. It gets lower and lower and lower. And because of this, the algorithm does not work properly, and it becomes unstable. So there are some solutions. One of them is to clip the gradients during backpropagation so that they never exceed a certain threshold. It can be resolved by the different activation functions to be used. You can also carefully model the learning rate and loss function. Now, you have a model now, so what do you do? Well, there's this thing called the constant confusion matrix, and what basically that does is that it gives you an evaluation of how successful your model has been. Okay, the General ones that are always used are accuracy, precision, and sensitivity. The other ones are used also, but these two are the most common ones. So accuracy is the overall effectiveness of a classifier. Precision is class agreement of the data labels with the positive labels given by the classifier. And sensitivity is effectiveness of a classifier to identify positive labels. So now I have given you all the tools to create a deep learning model from scratch. Okay. However, for the past decade or so, researchers have come up with clever architectures to accomplish specific tasks. So you don't have to reinvent the wheel. You can use these learning models instead. In the following slides, I will present to you, in a very high level, the different learning models, namely CNN, LSTM, GANS, Autoencoder, and Transformer. So CNN, as a background, is a deep learning model that consists of several significant layers. We have the input, which is a 2D image, and we have convolution pooling, that there's combination that's followed again and again. Convolution, basically what it does is that it takes a subgrid of the image, and it performs a calculation on it. Okay, so that's convolution. Max pooling, what it does is that it takes a grid of the data from the convolution layer, and at each subgrid, they pick just the maximum value. So this condenses the number of variables. After this feature learning issue, it's sent to a classifier, which determines if it's a car, truck, van, dog, and so on. Now, how this works is that in the feature learning, using convolution and pooling, you end up extracting features from the images. So for example, edges, color, positions of eyes, and then based on these feature learnings, it is then combined and classification is possible. So CNNs are very, very popular since 2010 because there's this ImageNet competition. Okay, it's a yearly competition whereby millions of images are, as a data set, is trained a model to be able to predict what the images are. So in 2012 we had AlexNet, in 2014 we had GoogleNet, and then in 2015 up until now, the error for classification has been less than the human error. So that's very important. So some famous applications of CNN: image recognition, video analysis, natural language processing, anomaly detection, drug discovery, health risk assessment and biomarkers of aging discovery, checkers game, Go, time series forecasting, cultural heritage, and 3D datasets. So in 2017, my paper towards Alzheimer's disease classification through transfer learning was accepted into IEEE, International Conference of Bioinformatics and Biomedicine. And here, basically what I did is that I took a model that won ImageNet called VGG16, and I trained it to detect Alzheimer's. I did it in two ways. I did it in one way using the weights learned from the ImageNet combination, and the other way where I trained it from scratch. And I found out that indeed with transfer learning, you're able to get a better accuracy, faster, and much higher. Now I'm going to talk about LSTM. So LSTM belongs to the recurrent neural networks, okay? And recurrent neural networks are basically neurons that loop. They produce an output that is sent to the next cell, okay? So LSTM was created. It does the exact same thing. It sends the data from the previous cell to the next cell to preserve history. However, the LSTM solves the vanishing gradient and exploding gradient problems of RNN. And this is accomplished because it has several gates. They have an input gate, forget gate, output gate, cell gate, history gate. And all of these gates, they help to make historical learning, sequential learning much better. So there's other models, and I'll just talk about the people model. So in this model, actually, they just create another, they add what's called people connections to allow the gate to utilize the previous state as well as the previous hidden state. So it helps to learn better than LSTM. So this is a version. I have not used this myself, so I don't know exactly how it works. So some famous applications include robot control, time series prediction, speech recognition, rhythm learning, music composition, grammar learning, handwriting recognition, human action recognition, sign language translation, protein homology detection, and so on. Now I talk about GANS. GANS is a very, very revolutionary neural network. What it does is that it doesn't train in the conventional sense of subtracting the uh, loss, the target from each other. And instead here, what happens is that you have two main neural networks. One is called the generator and one is called the discriminator. So the generator takes a distribution and adds noise, okay, and it sends to the discriminator. And the discriminator has a real-world image, and it tries to determine if this image created by the generator is real or fake. Real means it belongs to the dataset, and fake means it does not. So what can this be used for? Uh, there's the case where you send to the generator some random bits of information, and then the generator, because of this GAN's training, is able to create a portrait of a person that never existed before. It's a totally unique, new image of a person that does not exist. And these are the accomplishments of GANs. It's able to do something like that, and to such a high degree. So there's many, many different models of GANs. Some extend CNN architecture, and so on. So there's lots. There's DC gun, C gun, info gun, stack gun, pix to pix, psychogan, which translates images from a source domain to a target domain. So there's lots and lots of variations here that we can explore. Other applications include detecting glaucoma, producing photorealistic images, such as interior designing, industrial design, shoes, bags, clothing, forensic facial reconstruction, age face photographs, aging with time, data augmentation, speech to face, can construct an image of a person's face after listening to their voice, and so on. So here's an example of GANs. This is called a deep fake. And what a deep fake is a video of a person in which their face or body has been digitally altered so they appear to be someone else, typically used maliciously or to spread false information. So that was a very, very interesting and exciting video. You saw at the end that there was somebody else completely different, with a different voice, with a different face, and was able to produce this really, really lifelike Obama. So that's the power of GANs. Okay, now I'm going to talk about the autoencoder. So the autoencoder is consisting of two major parts. The first part is the encoder, which takes an input and condenses it to the latent space, which is the center, and then it decodes it to the output, and the output should be the same as the input, okay? So essentially what's happening here is that we are reducing the input to their fundamental factors, okay? Just like when you factor a number, you break it down to its fundamental characteristics, and this is exactly what happens here. So there's three types of autoencoders: regularized, concrete, and variational. Um, There are different types of application, including dimensional reduction, image compression, image denoising, feature extraction, image generation, sequence prediction, recommendation system. The next we have is a transformer. A transformer uses the idea of attention mechanism instead of recurrent networks, and it has been a huge revolution. And basically, what attention net does is that it takes the data and tries to focus the attention on the important concepts. Okay, before with recurrent learning, what happens is that we memorize the whole history. But you see, that's not necessary. In fact, that's too much work. With the attention network, we just focus on the specific topics that are important. So we have this thing called a query key and value. So for example, when you search query for a particular video, the search engine will map your query against a set of keys, video title, description, so on, associated with possible stored videos. Then the algorithm will present you with the best match videos values. And this is the concept of feature-based lookup, which is the concept of attention mechanism. Another issue with this transformer that's important to learn is not only the attention mechanism, but it's based on encoder-decoder as well. The first part on the left is the encoder, and the second part is the decoder. So there, as I said, there has been explosion of transfer models, and here's a big overview. They love Sesame Street, so this is why it's all with Sesame Street. So we have Bert model, Elmo model, Ernie model, and so on. Each one of these models have had some sort of very, very important contribution. So some famous applications: machine translation, document summarization, document generation, named entity recognition, biological sequence analysis, and video understanding. So now what? I have given you all the tools, all the models. Now what? What is there more to learn? Well, I'm going to talk about ensemble learning, transfer learning, hybrid, and Python. So ensemble learning is the case where your model is not working properly, and how can you make it better? Okay, so ensemble learning, the ensemble means that you take more than one model. Okay, so we have the stacking, which is that you have different model algorithms and you add them together. We have the bagging, okay, where we take the different algorithms and we average them together, okay, and we have the boosting, whereby what happens is that you take the models and you stack them together. So the result of one model passes to another model, passes to another model. Generally, from my readings, is that when they seek to improve, ensemble is a method that many people do. There's also transfer learning, which I alluded to earlier when I talked about my Alzheimer's project. Basically, transfer learning is taking a trained model and retraining it. So, for example, in my case, the CNN was trained on ImageNet data. So instead of retraining the CNN from scratch, I took the trained weights and used it for my final project. Hybrid. Okay, so we learned LSTM, we learned CNN, we learned GANS. But that's not the only thing. You can combine these models together. So in this example, I combined CNN with the LSTM for gold price forecasting. So CNN is used for what it's built to use, and that is extract important information. Okay, the LSTM is used to make sequential predictions of price, right? As we learned, LSTM is good for sequential. So this is just an example. So if you see in the literature, lots of times the authors combine different types of models. And we also have Python. Python would probably be the go-to library, programming language for machine learning, deep learning. And why is that? It's because it's open source, it's freely available, and not only that, but the machine learning and deep learning community has adopted these models as status quo. So with these models, you don't have to recreate functions such as LSTM. They're already usable libraries. You can build them from scratch, but you don't have to. So before you program, to save time, check the libraries for a ready-made function. and it will save you lots and lots of headaches. Now I talk about deep reinforcement learning. So basically, in deep reinforcement learning, we have an agent that takes an action in an environment. This environment updates the state, and the agent gets a reward. Okay, this is repeated again and again and again. That is the basis of reinforcement learning. Now we have deep reinforcement learning and regular reinforcement learning. So what's the difference? With regular reinforcement learning, the state and action is sent to a table, and this table determines the value. Okay, so the state and action will combine. If I am in this state, and the next action is this state, what is my value? Okay, so traditionally this was done with a lookup table of states and actions. Okay, but what happens is that this table can become impossibly huge. So a way to solve this is to use deep Q learning. So replacing this table with a neural network. Okay, now the fundamental equation to learn deep reinforcement learning, and this is done before actually uh, using the deep reinforcement learning, is that you update the model, the Q table, the Q neural network, based on the following function. We take the current values and we add it to a reward plus a maximum future reward and also the current value, and we multiply that by the learning rate. So the learning rate just means how much, uh, how quickly the future rewards will impact the value, the current value. And the discount rate, what you have to know is that part of deep reinforcement learning is that they discount much more values that are long term than values that are short term. And it just makes sense, right? You value stuff that's closest to you than further away. There's also the issue of exploration and exploitation. So you can train the model to be more exploration, which means it searches for new information, new paths that have not been sought before. You can also have exploitation, which is you focus on the knowns. And that's basically deep reinforcement learning. So the different models, there's two. Uh, there's two. One is you can use has a deep Q learning neural network. Okay, and this new deep Q learning neural network can be different neural networks. Can be CNN, LSTM, GANS, and so on. So there's several applications. The famous ones probably self-driving cars, gaming, engineering, healthcare. It can be applied to different fields: healthcare, education, transportation, energy, business management, science, engineering, art, natural language processing, computer vision, robotics, games, computer systems, finance, and so on. I guess the most famous one is AlphaGo and AlphaZero. This is a company, this machine, reinforcement learning machine, was able to build the Go, the professional, the best Go human player in the world. Okay, and it did it all by reinforcement learning. So actually, what it did is that it played games by itself at first, and then it learned more and more and more complicated issues. So it's just amazing that this was able to accomplish such a high level just with deep reinforcement learning. So now the power systems. So I talk about power system smart grid. In 2015 to 2012, if you consider all the literature, okay, on the left, these are the percentages that different uh, architectures have been done. For example, GAN has been 2.9%, GRU has been 2.1%, CNN has been 37%, RNN has been 14.8%. The applications for the power grid include load prediction, microgrid management, demand response, anomaly detection, power system analysis control, cybersecurity, renewable energy prediction. Okay. Also, there's a hybrids as well, as I told you before. And these hybrids include CNN, LSTM, CNN GRU, and the other ones as well. If you look at the frequency of the deep learning and smart grid terms from books from 1980 to 2020, we see that there has been a huge frequency of the terms of a smart grid and deep learning within the past decade. There has also been several review papers that talk about deep learning. So the current paper, this is based on this deep learning application for smart grid, and there's also forecasting models for buildings, and so on. As well, these are different architectures that I told you before have been used. So these have been used. These are the mainstream deep learning architectures and their advantages and limitations. So now, what is the future? So probably within the next 5 to 10 years, we're going to see an explosion of quantum computing. It's getting there. The research is already quite convincing, but there has been lots of research on the ideas and theories around quantum computing, but the feasibility yet has not been truly successful. But anyways, what happens now is that quantum computing will not replace everything. There are certain tasks that are much better executed using classical computing instead of quantum computing. So we're going to have a hybrid of quantum computing, classical computing together for lots of tasks. As well, the main fundamental issue, the difference between classical machine learning and quantum machine learning, they're basically the same, except that classical computing is 0 and 1, and quantum computing is between 0 and 1. But in terms of machine learning, we have the mathematical algorithms, the pattern recognition, and it's just how this machine learning is done that's going to be the big game changer. So this presentation, I had several resources, some very good ones. Deep Learning by Ian Goodfellow. This is a classic. Ian Goodfellow is the student who did GANS. There's Deep Learning with Python by Francis Chalot. He's the creator of Keras. There's also Hands-on Machine Learning with Scikit-learn and TensorFlow. This is also a very good book as well. There's also lots of journal articles. Papers with Code is about deep learning models that have code easily available papers. The next three from GitHub, they have lots of interesting papers to read. I read them. I read quite a few, and they're very good. The paper that I covered a lot regarding smart grid was called Deep Learning Smart Grid Technology, a review of recent advances and future prospects. And also have this really wonderful online course from YouTube MIT. I watched it and I highly recommend you to do that. Thank you everybody for your attention. I had a wonderful time teaching this course and I hope you learned a lot. Thank you.